Welcome, everyone. Ready to dive deep. Today, we're tackling something we think we understand. Reality. Seems simple, right? What we see, what we touch. But when we look at it through the lens of quantum physics, well, it gets kind of mind-blowing.
Totally.
Yeah.
It kind of throws everything we thought we knew out the window.
Right. And I know a lot of you listening, like me, are curious folks wanting to understand the world around us as quickly but thoroughly as possible. You might have some ideas already about what's real.
I'm sure you do.
Well, get ready because today we're going to shake those ideas up a bit.
Just a little bit. And for this deep dive, we're going to be looking at a fascinating book by Paul Davies. It's called Other Worlds, and it's all about space, hyperspace, and, you guessed it, the quantum universe.
So in this deep dive, our mission, should we choose to accept it, is to unpack how quantum mechanics basically challenges our everyday understanding of existence. You know, those big existential questions.
Exactly. Like, what is reality really? Are there parallel worlds?
Yeah.
And does the observer actually create reality? All pretty big questions, if you ask me.
Huge questions. And we're going to explore them all, plus delve into the fundamental uncertainty that seems to govern the universe at its most basic level.
Absolutely.
And don't worry, we're going to do this in a way that doesn't leave you feeling like you've just, sat through a quantum physics lecture.
To try to keep it light, so to speak.
Exactly. We'll try to keep it as fun and engaging as we possibly can. Okay, let's start at the beginning. How does this quantum revolution actually upend our notion of reality? This is where it gets really interesting. Turns out, at the atomic and subatomic level, particles, they aren't exactly things in the sense that we understand that word. They don't have this well-defined independent existence until they're actually observed.
Yeah, it really makes you question what we mean by existence, doesn't it?
It really does. Think about it. You, listening to this right now, you're made of atoms, right?
Last time I checked, yeah.
Yet at that fundamental level, things aren't as solid as they seem. I mean, is the simple act of trying to understand your atomic makeup fundamentally changing it?
You're getting into some pretty deep philosophical territory there, but that's exactly the kind of question that quantum mechanics forces us to confront.
Right. And Davies points out something really fascinating in his book. He says that reality, to the extent that word actually means anything, isn't a property of the external world by itself. Instead, it's what he calls intimately linked to our perception of the world, to our presence as conscious observers.
Exactly. It's like the universe is waiting for us to look at it before it decides what it wants to be.
And this puts the observer not as a mere spectator of the cosmic drama, like we thought in previous scientific revolutions, but back in the center stage. And that has some pretty big implications for how we understand the universe, don't you think?
I think it's huge. It really shifts the whole paradigm. And some scientists have even gone so far as to suggest that the observer's consciousness, the active information entering our awareness, that's the fundamental step in the creation of reality.
Like we're literally creating reality just by observing it.
Taken to the extreme, yeah. Imagine the universe only achieving concrete existence as a result of our perception. Kind of boggles the mind, right?
Totally boggles the mind. I mean, that's a radical idea, but is there any evidence to support it?
Well, whether or not we accept these ultimate paradoxes, I think most physicists would agree that at least at the atomic level, matter is held in this kind of limbo of possibilities. Davies calls it irreality, until a measurement or observation is made. It's like the atoms are between worlds, undecided about where to go.
So until we measure it, it's not really anywhere.
Kind of. Think of it like a coin spinning in the air. It's neither heads nor tails until it actually lands. A quantum particle in superposition, it's in a similar state of having multiple possibilities simultaneously until we actually look at it.
So that leads to a really intriguing question. Is this quantum limbo confined to the subatomic world? Or could it erupt into our macroscopic reality and even into the cosmos?
Yeah, that's a good question. Like, how far does this quantum weirdness extend?
Davies actually mentions the famous Schrodinger's cat and Wigner's friend paradoxes, and these thought experiments really explore this question of the true nature of reality. I mean, could this quantum maybe seep into our everyday world?
It's a possibility, and it ties directly into the next central point, this inherent uncertainty in the subatomic world.
Okay, so let's talk about uncertainty. I mean, us humans, we have this deep-seated desire to believe in determinism.
We'd like to think we have some control over things.
Absolutely, that every event has a prior cause and the world unfolds according to this orderly scheme, governed by laws. This idea, as Davies points out, it even forms the basis of a lot of religions. Why do you think we cling so tightly to this idea of a predictable universe?
I think it's a comfort thing. Makes us feel safe, like we understand how things work.
Right, and that's where quantum mechanics throws us a curveball. Even Einstein, of all people, he resisted quantum theory because of this element of randomness. His famous, quote, "God does not play dice," perfectly sums it up.
He was a firm believer in a deterministic universe. Everything happens for a reason.
So what bothered him so much about this uncertainty?
I think he just couldn't accept that the universe could be fundamentally random.
But it seems like it is, right? I mean, we all understand that life can be arbitrary and that predicting the future of complex systems like the weather or the economy with any real accuracy, it's impossible.
Right. There are too many variables.
But most people still believe that in principle, the world is predictable if we just had enough information.
Like, if we knew the position and velocity of every particle in the universe, we could predict everything that would ever happen.
That was kind of the prevailing scientific viewpoint for a long time. Even physicists used to think that atoms obeyed these fixed rules, moving according to some precise system, like clockwork. Isn't that a comforting idea?
It is. It's nice to think that the universe is orderly and predictable.
I mean, think about Laplace. 2 centuries ago, he said that if you knew all the atomic motions, you could map out the entire future of the universe.
A pretty bold statement.
Right. But the discoveries of the 20th century revealed that nature has this rebellious side.
It likes to keep us on our toes.
It really does. Inside the seemingly law-governed cosmos, there's this randomness, this microscopic anarchy that throws that clockwork predictability out the window and introduces this absolute uncertainty into the world of the atom. So the universe we perceive, is it just an accident?
It's a question that has haunted physicists and philosophers for decades.
I mean, is it chance or is it choice? Is the universe we perceive merely an accident, or did we somehow choose it from this, bewildering array of alternatives?
It's a pretty mind-bending thought, and it leads us to the idea of the many worlds.
Okay, so let's talk about this many worlds thing.
Right. Davies mentions that to avoid this whole observer problem, you basically have to accept this multiple reality of parallel worlds.
Whoa, hold on. Multiple realities, that's a lot to take in.
Or you have to deny that the real world exists at all, independent of our perception of it. Pick your poison, I guess.
So either there are infinite versions of ourselves living in parallel universes, or the reality we experience is just an illusion created by our minds.
Yeah, those are pretty much the options on the table.
Wow. Okay, let's unpack this a little bit. What's so radical about this idea of parallel worlds?
Well, the basic idea is that every quantum event, every decision at the subatomic level, could lead to a splitting of the universe into multiple branches, and each of these branches represents a different outcome.
So every time an electron does its quantum thing, a new universe is born.
Exactly. So think about it. Every choice you've made in your life, big or small, could have spawned a whole new universe where you made a different choice.
That's a lot of pressure. Am I living the best version of my life right now?
Who knows? Maybe in another universe you're a rock star. But we'll get deeper into this when we talk about Everett's interpretation later on. For now, it's crucial to understand that this is one of the ways that some physicists try to deal with the strangeness of quantum mechanics.
It's definitely a strange idea. But let's shift gears for a second and talk about observation as interaction.
Sure, observation is key in quantum mechanics.
Because even the most seemingly passive act of observing actually requires something to interact with what we're observing. Davies uses this great example. When we observe Jupiter, it's photons of sunlight reflecting off its atmosphere that travel all the way to our eyes, and through a chain of interactions give rise to the sensation in our brain.
Right, so even just looking at something as far away as Jupiter is actually a physical interaction.
Exactly. There's always something going on behind the scenes, even when it seems like we're just passively observing.
And what's important to remember is that this interaction always has a reciprocal effect. The act of observing inevitably perturbs the observed system. It's the action-reaction principle at play.
To get information, we have to affect the thing we're trying to get information about.
Precisely. Think about everyday examples. To measure an electric current, we insert an ammeter, which slightly hinders the flow of current. To measure the brightness of a light, we absorb some of its radiation.
Or even to measure the temperature of a liquid with a thermometer that causes the liquid to cool slightly. We're always, in a way, touching what we observe.
Right. Our access to physical systems is always mediated through what Davies calls probes. Even when we see a distant star, it's the photons interacting with our eyes that give us that information.
There's no observation without interaction.
Exactly. It's like trying to measure the pressure of a tire by letting out some air. The act of measuring changes what you're measuring.
Which has pretty profound implications when we get to the quantum level, where the classical concepts we take for granted just start to break down.
Right, things get really weird at the quantum level.
They do. Attributes of subatomic particles, like position and momentum, they're not always well-defined until they're measured. It's Heisenberg's famous uncertainty principle in action. We can't know with absolute precision both things simultaneously.
It's like the more we try to pin down one aspect of a particle, the more elusive the other aspect becomes.
Exactly. And it's not just that. The order in which we make measurements matters a lot at the quantum level. If we measure an electron's position and then its momentum, we get a different result than if we first measure the momentum and then the position.
Which is crazy. In the classical world, the order wouldn't affect the outcome at all. It'd be like asking someone their age and then their favorite food, and getting different answers than if you asked their favorite food first and then their age.
Right. It's as if we're trying to describe something that just doesn't behave according to our everyday intuitions.
Because at the quantum level, the act of measuring actually influences the thing being measured.
Okay, so measurement itself is a kind of interaction that changes things. And Davies also mentions other pairs of incompatible quantities, like energy and time. Measuring a system's absolute energy, that would require an infinite amount of time.
It's like trying to measure something that's constantly changing.
Yeah.
You can never get a truly accurate reading.
So these limitations, they're fundamental in quantum mechanics.
Yeah, it means there are inherent limits to what we can know about the universe.
And it's crucial to remember that this quantum realm, with its wave-particle duality and its inherent uncertainties, it's not just for tiny particles.
It's the foundation of everything.
It applies to all matter, even us, at a fundamental level. It's just that the effects are so minuscule in our everyday life that we just don't perceive them.
It's like the quantum world is operating on a scale that's just too small for us to see directly.
Right, like we don't see the wave properties of a soccer ball, for instance, because its wavelength is incredibly small.
It's just too big and bulky to exhibit those quantum effects that we see in tiny particles.
But even though we don't perceive it directly, quantum mechanics has very real applications.
It's more than just theory.
Davies mentions the electron microscope, which uses the wave nature of electrons to achieve these, huge magnifications, much greater than conventional light-based microscopes.
It's a real-world example of how this strange theory actually has practical consequences in our technology.
Absolutely. And then there's the concept of quantum tunneling, where particles can actually pass through energy barriers that classically they shouldn't be able to overcome.
Like it's magic. A particle just appears on the other side of a wall, even though it didn't have enough energy to get over it.
It's like a ball being able to go right through a solid wall.
Yeah, it's pretty counterintuitive. But Davies explains this is possible because particles can borrow energy for very short periods, courtesy, again, of Heisenberg's uncertainty principle. It's like they have this little window of opportunity to do something impossible.
And an important example of this quantum tunneling is radioactive decay, right?
Right. It's a probabilistic process governed by the ability of particles within the nucleus to tunnel through the barrier of the strong nuclear force.
So that explains why radioactive materials have this predictable half-life.
Exactly. So this quantum effect, it's behind something as common as carbon dating.
Now, Davies briefly introduces this enigma of quantum entanglement. He mentions the Einstein-Rosen-Podolsky paradox, which we'll explore in more detail later. But basically, it points to these strange correlations that can exist between distant particles.
Correlations that seem to defy our classical understanding of cause and effect.
Right. It's like if you had two coins and you flipped them at the same time, they would always land on opposite sides no matter how far apart they were.
It's a spooky action at a distance, as Einstein famously called it.
And this uncertainty that we've been talking about, it's not limited to matter. Davies tells us that it also controls the very structure of space and time themselves.
Wow. So space and time aren't just this static backdrop for the universe.
Nope. They're active participants, capable of changing shape and extent.
It's like they're alive.
Right. At the ultramicroscopic scale, space-time could have this, hollow and foamy structure, full of tunnels and bridges. It's what's known as quantum foam. So our universe at that fundamental level could be a maze.
It's like the reality we're used to dissolves into something far stranger and more dynamic when we zoom in close enough.
Exactly. And our experience of time, it's closely linked to our perception of reality. Any attempt to construct a real world has to confront the paradoxes of time, which Davies explores in depth in his book.
Right. It makes you wonder if our linear perception of time, past, present, future, is just an illusion.
It really does. And it brings us to the idea of multiple paths to the future. Davies explains that just as a thrown ball can follow an infinite number of trajectories, the universe as a whole follows an infinite diversity of trajectories into the future.
So the universe is constantly branching out into different possibilities.
It could be. The initial conditions are what determine which of those trajectories actually gets taken.
And that raises some fundamental questions about the beginning of the universe. Modern cosmology suggests that the universe hasn't always existed, which implies a creation event some 15 billion years ago. So what initial conditions led to the universe we observe?
I mean, were they special or were they general? And what other universes could have risen from different conditions?
It's like asking why a particular seed grew into a specific oak tree and not some other kind of tree.
And the philosophy behind all of this, as Davies points out, is that our universe could be just one of an infinite set of possible universes, a particular path into the future.
So all those other ghostly worlds, they might not be mere academic curiosities, but could have real effects on the universe we know.
Wow, so we could be feeling the influence of these other universes without even realizing it.
It's possible. And Davies also touches on the observer and free will at this point. The Newtonian view seemed to diminish our participation in this deterministic universe. But the quantum view, with the observer playing a role in shaping reality, it suggests the possibility of restoring free will.
So maybe quantum mechanics gives us back some agency in the universe.
Maybe. It's a question we'll explore further later on.
All right, let's tackle head-on this whole nature of reality and how quantum mechanics really challenges our basic intuitions.
Sounds good. It's one of the most mind-blowing aspects of quantum theory.
Davies is very clear that there is no universal agreement among physicists and philosophers about the nature and existence of reality. So what is real to you?
That's a big question. But I think our common intuitive view is that there's this external world of things that exist independently of whether we observe them or not. Mount Everest, the Andromeda Nebula, electrons, all these things existed before we were here to contemplate them.
They were just doing their thing, waiting for us to show up.
Exactly. It's the idea of an objective universe out there waiting to be discovered.
But Davies points out that our direct experience is always an interaction between the observer and the observed, and it's colored by our internal models and expectations. In everyday life, we don't experience a purely objective reality, but this mixture of internal and external perspectives.
Right, like our perception of color, for example.
Yeah.
It's a construction of our brains. It's not an inherent property of the objects themselves.
Okay, so there's no escaping our own subjectivity.
I don't think so. And the goal of the physical sciences has been to build a model of reality that's independent of the observer. But even in Newtonian mechanics, observation inevitably perturbs the observed system, however infinitesimally, like light affecting planetary orbits.
So there's always some slight influence of the observer on the observed.
There's no way to completely separate ourselves from the experiment. We're always a part of it.
So how did the Newtonian view see the observer?
It presented us as just another part of the cosmic machinery, with predetermined roles. A central feature was the existence of identifiable things with intrinsic attributes.
Like a football is always a football, no matter who's looking at it or how they're looking at it.
Exactly. It was this vision of the universe as one big clockwork mechanism.
But quantum theory drastically changes this picture, especially at the subatomic level.
Things get very fuzzy down there.
Observation has these dramatic effects on tiny particles. Davies reminds us that it's impossible to simultaneously attribute an exact location and an exact motion to an electron.
Yeah, like trying to catch a tiny speck of dust. The very act of trying to touch it pushes it away.
And there's also this difficulty of assigning an independent existence to identical particles in a mass. Like, when electrons get close enough, we can no longer tell which is which because their locations can be more uncertain than the distances between them.
It's like they lose their individual identities and become part of this collective quantum soup.
And let's remember the double-slit experiment. We can't always say which slit a photon or electron really passed through.
It's as if the particle takes both paths simultaneously until we observe it.
Some have tried to imagine this underlying deterministic reality with hidden variables influencing quantum behavior, similar to the unknown factors affecting a coin toss.
Right, but this hidden variable theory isn't widely accepted.
Why not?
Because it requires these complex, undefined underlying forces, and also because of the profound implications of certain subatomic experiments. It seems like uncertainty is fundamental, not just a matter of our ignorance.
Okay, so it's not just that we don't know enough, It's that there's something inherently unknowable about the universe at the quantum level. Which brings us to the Einstein-Rosen-Podolsky paradox, the famous EPR experiment, and this concept of quantum entanglement in more detail.
All right, let's dive into entanglement. This is where things get really spooky.
Davies explains it using entangled particles, like two polarized photons. They can be linked in such a way that measuring a property of one instantaneously influences the property of the other, no matter how far apart they are.
It's like those two coins I mentioned earlier. They always land on the same side, even if they're light years apart. If one lands heads, the other instantaneously also lands heads.
So what's so mind-blowing about that?
What's mind-blowing is that this correlation seems to happen faster than any signal could travel.
So it seems to violate Einstein's theory of relativity.
If it were interpreted as a direct causal influence, then yes.
So how do we reconcile this with our understanding of physics?
Well, the key is that the outcome for each individual particle is still random. This maintains consistency with quantum uncertainty and prevents faster-than-light communication. So information isn't being transmitted instantaneously.
But the correlation between the particles is undeniable.
It's like they're connected by some invisible thread that transcends space and time.
So what does this tell us about the nature of reality?
The implication is that subatomic uncertainty isn't just due to our ignorance. It's inherent to nature itself.
It's like the universe is playing dice with reality.
Davies emphasizes the difficulty of maintaining this realist view where the photons have definite polarizations before measurement, as this would contradict experimental results. The quantum wave describing the photon must be a superposition of possibilities. So before we measure it, the photon is, in a way, in all polarization states at once.
Okay, so before we observe it, the photon is in a state of maybe. And that's where the Copenhagen interpretation comes in.
Right, this perspective holds that a quantum system exists in this superposition of states until it's measured, at which point the wave function collapses into a single definite state.
So it's like a blurry photograph suddenly becoming sharp when it's developed.
The act of measuring forces the system to choose a state.
So before observation, it's like it's meaningless to ascribe a concrete reality or even definite alternatives to the quantum world.
It's in this nebulous state of pure potentiality.
It's a superposition of worlds, right?
Exactly. And Davies quotes Niels Bohr, one of the fathers of quantum theory. Bohr said that there are basic limitations, which atomic physics perceives, in the objective existence of phenomena independent of the means by which they are observed.
So according to this interpretation, reality only exists when we look at it.
It's as if the universe is waiting for us to observe it before it decides what it wants to be.
That's a pretty profound statement. So in this view, reality only has meaning within the context of a measurement or observation.
Right. We can't say how a particle was really behaving before we measured it.
It's like asking what the color of a shirt is in a dark closet. It doesn't really have a color until you shine a light on it, and the only true reality is the total system, right?
Exactly. Subatomic particles plus the apparatus plus the experimenter.
So it's all interconnected.
And the observer's choice of experiment, for example, which angle to set a polarizer, that changes the available alternatives and thus influences reality.
So the way we choose to look at the universe determines what we see.
In a way, yes. It's like saying that the type of lens we use on a camera determines the kind of picture we take.
Now, Davies brings back Hugh Everett's many worlds interpretation as this radical alternative. Instead of this collapse of the wave function, Everett takes the mathematical description of quantum mechanics literally.
He restores reality to the wave function and to the superposition of states.
So instead of collapsing, reality branches.
Precisely. In Everett's view, no special collapse occurs upon observation. Reality is always there, encompassing all possibilities. When a measurement is made, the universe doesn't collapse. It splits into multiple universes, each representing a different outcome.
So both possibilities become real in the respective branches. So if I flip a quantum coin, it doesn't land on either heads or tails.
Nope. The universe splits into two, one where it lands heads and one where it lands tails.
So every time a quantum event happens, the universe is splitting into countless copies of itself.
That's the basic idea. And Davies connects this back to this idea of the superworld, that our observed world is this three-dimensional subspace of a higher dimensional hyperspace containing infinite possibilities.
So is there a version of me listening to this very show in another universe?
Maybe. And the statistical probabilities we see in quantum mechanics, they arise naturally in this interpretation. We only experience one branch of the universe. and the information about the other outcomes is just inaccessible to us in our branch. The hyperspace as a whole is deterministic. The randomness comes from our limited perspective. There could even be duplicates of ourselves in other universes, living slightly different lives.
Okay, so it's not that the universe is random, it's that we only see a tiny slice of the total reality.
Exactly.
Which brings us to the anthropic principle. Davies introduces it as this idea that the universe must have certain characteristics because if it didn't, we wouldn't be here to observe it.
It's a pretty mind-bending concept.
It really is. So our very existence imposes certain conditions on the universe.
That's the basic idea.
What are the different types of anthropic principles?
Well, there's the weak anthropic principle, which states that observers will only observe universes consistent with their existence.
That one seems kind of self-evident.
It is. And then there's the strong anthropic principle, which suggests that the universe must have properties that actually allow for the development of life.
Okay, so the weak one is almost a tautology, and the strong one is a much deeper claim.
Exactly. And Davies explains how the many-world interpretation provides this framework for the anthropic principle.
How so?
We inevitably find ourselves in a universe that supports life, because we couldn't exist in those that don't. Our existence selects the kind of world we inhabit from this infinite variety of possibilities.
So it's like saying that we can only see the fish that are in the water because we can't breathe underwater.
Exactly. And that raises the question of how finely tuned the universe actually is for life. How much could its characteristics actually vary and still allow for us to be here?
So we're talking about the Goldilocks zone, but on a cosmic scale.
Exactly. And Davies stresses the importance of both the laws of physics and the initial conditions in determining the nature of a universe. He even wonders if the laws themselves could vary in different branches of the hyperspace. Could there be universes with completely different laws of physics?
That's a pretty wild thought. And Davies gives some fascinating examples to illustrate this fine-tuning. Like the delicate balance of the fundamental forces like gravity and electromagnetism is crucial for the existence of stars, atoms, and ultimately life as we know it.
Right. If the strong nuclear force were slightly weaker, only hydrogen could exist. And if the electromagnetic force were much stronger, atoms couldn't even form.
So it's like this cosmic tightrope walk.
It really is. And the anthropic principle offers an explanation for the apparent improbability of these forces in our universe. We could only exist in a universe where they're tuned appropriately for life.
So maybe it's not so much that the universe is fine-tuned for life, but that life is fine-tuned to the universe.
Exactly. We are a product of our environment on a cosmic scale.
And even the number of space and time dimensions, as well as the masses of the subatomic particles, they all seem to be delicately balanced to allow for life.
It makes you wonder why there are 3 spatial dimensions and 1 time dimension. Could life exist in a universe with more or fewer dimensions?
Okay, finally, let's talk about the beginning and the arrow of time.
Right, time. The big mystery.
Davies discusses the Big Bang and the highly uniform and ordered state of the early universe. And this initial order is actually necessary for the existence of a clear distinction between past and future, which seems to be crucial for complex systems like life.
Right. Why do we remember the past but not the future?
It's one of the big unanswered questions. And life and our existence, they depend so delicately on this initial cosmic structure, like the relative uniformity of cosmic matter, that prevented immediate collapse into black holes.
Right. If the early universe had been just slightly more clumpy, everything would have collapsed into black holes before stars and galaxies could even form.
Davies contrasts our ordered universe with the possibility of other universes in the hyperspace that could be disordered or even have the arrow of time reversed.
What would it be like to live in a universe where time runs backwards?
That would be crazy. I wouldn't want to experience that.
Me neither.
What's really mind-blowing is that the fundamental equations governing the quantum evolution of the hyperspace are time reversible. The past-future asymmetry that we experience might not be fundamental, but it emerges in specific branches that can support life.
So our ordered universe could be just this local bubble within a predominantly chaotic cosmos.
We only observe it because our very existence depends on these benign conditions, so our ordered universe might be the exception, not the rule.
That's a pretty humbling thought.
So, to sum up this deep dive, we've seen how quantum physics radically challenges our intuitive understanding of reality.
It really turns everything on its head.
The observer seems to play this active role in shaping what we consider real. Uncertainty is inherent to nature. There are these mind-boggling possibilities, like parallel universes. And the anthropic principle makes us question why our universe is the way it is. It's quite a different picture from what classical physics presents us, right?
It's a whole new way of looking at the world. And the nature of reality, it remains a subject of intense debate without any easy answers.
Right, we've just scratched the surface here. Quantum mechanics has given us these incredibly powerful tools to understand the universe at its most fundamental level. But its philosophical implications, they still have us pondering deeply about what it actually means to exist.
It forces us to question our most basic assumptions about the world around us.
Absolutely. And to leave you with one last thought, if our observations actually play a role in shaping reality, what are the implications for our understanding of consciousness and the very existence of the universe?
It's a question worth pondering.
We invite you to ponder your own place in this potentially vast and interconnected cosmos and to consider if the reality that